started. I think I went over both of these kind of announcements last time, but I believe it may have been before James was in and Miguel wasn't there. So let me go over them again. And sorry, Kira, you have to hear them again. The first of these, I just want to encourage you with all the encouragement I can muster to please, if you haven't registered to vote, please register to vote. You still got maybe a week or two before registration for voting is, well, I mean, you can register anytime, but in order to vote in this coming election, you still got a week or two before you can, so you can register. Please register to vote. Once you're registered to vote, then please vote. Now, my wife and I have already voted. We went down on a Friday afternoon a couple weeks ago and voted. So you can do that if you don't want to be in a crowd, if your work schedule is going to be tough on that day. Go down someday when you've got some time, go to the courthouse, and you can vote then, okay? But please get registered and please, please vote. I can't think of any election. I think every election is important, but this one is by far the greatest. And as I told the other class, I'm sick and tired of them bragging on, well, we had 47% participation in this election, as if that's something good. What that means to me, yes.
I can't vote, so.
Oh, okay, all right, I understand. But your heart's in the right place, I bet. So, yeah, yeah. But those who can vote, please do. And the but I get sick and tired of, like, they brag on 47% of the registered voters voted. Now I think in this election it'll be greater than that, but it's still going to be pathetic. And that means that 24% of the electorate chose our leaders, because if only 47% are voting, 24 is the majority of that, and they have just decided our leadership with that. That's not a democracy. We're way short of what we need to be. Okay, so I encourage that. Number two, I heard this since our class on Thursday, because all three of you were in the class on Thursday. The dean, academic dean, sent me an email saying they are beginning the process of trying to bring some classes back to campus. I don't know which classes, I don't know how they're going to do it. They just said all the classes will meet in large lecture rooms, spaced apart, plexiglass shields between the instructor and the students, all sorts of mess like this. And I'm not going to be teaching in the spring because I'm retiring on 1st of February. But if I were, I wouldn't be able to go to campus. I would have to continue, and I think they would want me to continue doing it remotely because my health situation does not allow that. But anyway, I was trying to get feedback, and I know I got it from Kira before. She was exactly the same way I am. But do the two of you have any feelings on whether you'd want to be on campus? Would you rather continue virtual classes? And what's more, what have always proposed is that students who have trouble having good internet or having good signal and that kind of stuff, I would, since the campus is open, students could go to campus and go to a computer lab and do their classes there in front of a computer on Lawson's campus. And if you're having to do it off a mobile device and the screen's small and you can't follow or it's hard to follow, then to me they should have been doing that all along, since they do allow students back on campus now and they got a lot of the staff back on campus. But it's just a real tough situation. So the two of you guys, have you got any preference on going back to campus, continuing virtual, or what? I'm just trying to get it. Yeah.
I'd rather go back to campus.
Okay, yeah. Were you here this morning? I think you were, weren't you? Yeah, right, you were, and you already said that. And James, were you there when I polled you earlier? I think maybe you came in later. Okay. All right. Anyway, I've got a pretty good feel for it. Okay, so last time, oh yeah, I guess that's all I had. Anything from y'all? Any issues, problems, concerns that you want to bring up?
No, no, but I got a question.
Surely.
So you think it's more possible we'll go to campus next semester?
Okay, it's not going to be total. It'll be just selected classes because they only have so many large lecture rooms. So they can only do a few classes, and I don't know how they're going to decide what classes go and what don't. I don't know any of that. I think they're just trying to to do something different, and you'll just have to see. I mean, we had to submit the schedule weeks ago, and at that time it was all virtual or online. There wasn't any on campus. There was some hybrid type stuff for the career technical education program where they have to do some lab work, hands-on stuff. They had to do that. So a few of those classes have been happening even last summer and this fall. So it's that was the first word I had heard from it was late last week, probably Friday. I got the email that said that we had a department meeting, and I'll just tell you the instructors are pretty much worried sick about it because, certainly if it's on campus, you still got to be able to, if I were on campus teaching, I would still have Zoom going and stuff like that for those students who can't get to campus because either they've tested positive or they're been exposed to somebody that's positive and they are quarantined and stuff like that. We're still going to be doing the virtual stuff, but we would be on campus. Okay, so if I were there, I'd still be doing that, and I think any class that meets has to do that. So a student can get, infected or exposed or something, and that would still be covered. But how in the world are you going to cover it if an instructor gets sick? Okay, especially if they get really sick. I know that one instructor in the math department did get a mild case of it. As far as I know, he was able to keep teaching or managing his class because he had a pretty mild case. His wife, however, had a very, very severe case, and if she had been an instructor, she would not have been able to continue teaching. So that's the part that is worrisome to instructors. What do they do if they do get really down? And this disease can throw you down. In my last class, one of the students had it, and he was quarantined for 2 weeks, but he had a very mild case. He was in class every day that he was quarantined. Ever since he been off quarantining, I think he missed one class, but while he was in, he was there every day and participated well in everything because he had a very mild case. But only few people really have that mild a case, and especially older people like faculty members tend to be far worse than the young people, even though young people can have very severe cases. I have a student in one of my other classes that had it this summer, and he missed the last part of his summer classes. He just couldn't go at all. He was that sick, and he's having to do clear incompletes in those 2 classes and do classes this fall. So it was quite a tough situation on him. So you can't ever tell which way it's going to go. So that's why we're asking. That's why it's being considered. But see, administrators, basically they can shut themselves in their offices and hardly interact with anybody. Staff can kind of do that, and they can keep distance. But boy, an instructor is going to be in a classroom with maybe 30 students or something like that. That's kind of hard, and especially if you think going in and out, you're going to be passing. There's going to be lots of things in the air. It makes for a tough situation. So that's why we're I was doing sort of a poll because I'm going to be in a meeting in a couple of weeks that I want to have some information behind me. And so far, I think I'll say that students are really wanting to be on campus, have classes on campus, but instructors, from what I was hearing from mine, do not, okay, because you know, their situations are so much tougher. And then too, a lot of them have kids at home, and if the kids are home, then so there's going to be a lot of virtual classes going on one way or another. But from what I hear, y'all would just as soon we base those virtual classes on campus rather than at home. So I can understand that, and I appreciate it. It's not going to be me though, because I won't be, and my retirement has nothing to do with the situation at all. I'll turn 70 in January. That's why I'm retiring. I think that's long enough. So I will be uh, going into retirement. Okay. All right. Yes.
Like your wife works at UAB. What about UAB? Do you know anything about that?
Yes. UAB is really doing some very positive things there. I don't know how they're doing all their classes. I know that they have done things like, the Bartow Arena where they play basketball. They have fixed that up as a wireless place, and students can sit far, far apart from each other and get homework done. They can attend class. They can do whatever they want to there. UAB is really, really good about monitoring. You can't come on campus that you don't have a temperature check. I think that's the same at Lawson. And if you have a temperature, you're sent home. But they follow up and they make sure you get a test. They make sure all the things do, and they're doing a tremendous job. I think everyone has to have on their cell phone what is called a pass, and you have to report every day, I believe it is, what your conditions are, if you're feeling any of the symptoms or things like this, um, and um, and so they're way ahead of the curve from most of the schools. So UAB, I would say, is probably one of the safest campuses you can go to. They've got the medical school there. They have they have really planned this thing well. We just don't have the resources UAB does, nowhere close. And I think what they're planning is probably modeled on that. And I think we're using and following some of UAB guidelines. So, but UAB, I think would be. My wife goes, into work not every day, but she goes in pretty regularly. Of course, she gets her temperature checked. She has to report in. If she doesn't report in every day, she's not allowed back on campus. She has a report on her phone. If she has any symptoms, if she's been exposed to anybody who had symptoms, she has to do all that. And as long as that happens and she doesn't have a temperature, she can go on campus. Everybody is masked, have to be masked on campus at UAB. If you're in your office by yourself, you can take your mask off. But if anyone comes to the door, anything, so it's incredibly, and I think they're keeping social distance and stuff. So they're doing a fantastic job there. And I think UAB, I can't remember the numbers of students they've had at UAB who have tested positive. It's incredibly low, and most of those from community. It wasn't from UAB. And places like Tuscaloosa, they've had to shut down the bars in the city of Tuscaloosa because students were spreading it so badly. And so they've had thousands of cases where UAB has maybe had a dozen or two. It's just night and day difference. So I would say if you are planning to go to UAB, that's one safe place to be. Okay, but you need to follow guidelines really, really strictly because they are serious about it. I don't know if that's what you were asking, but that's what I've heard so far.
I mean, yeah, I'm gonna go to UAB next semester. That's what I was asking.
Right. Okay. All right. So I think that's a very safe move, but you will be having to maintain great communications there. Okay. All right. Good deal. Any other issues before we move on with today's class? Okay. Now, where we left off last time, we had started example 1 on page, we're in chapter 2, first order differential equations, section 2.4, exact equations, and example 1 was solving an exact differential equation. And the first step is always to check and see if it is an exact differential equation. We did that part, okay? And this is the first one we've done like this, so let me pull up the whiteboard and proceed from where we were. If I can get the whiteboard to come up. Now what I'm going to do now is move y'all back to the side and move this taskbar that you can't see out of my way, and then move the whiteboard as far to the left and up as I can to get maximum white space. Okay, so here's the equation we are to solve, if I can get my pen to show up. Okay, here it is. 2xy dx plus x squared minus 1 dy is equal to 0. Okay. And folks, by the way, that's the standard form for setting up your exact equation. You've got to have an equal 0 on the right hand side. You've got to have a plus between the two differentials on the left hand side. Okay? We've already checked to see that the partial with respect to y of this first term, that would be 2x, is equal to the partial with respect to x of the second term, and that would be 2x. Those are equal to each other, so we can proceed. We did that last time. Now, what the next step is, and I'm going to try to follow the same way the book does. Remember what our model was. Our model was this. Partial of f, okay, wait, okay, let me start over. Here's what we're based on. We're assuming that there is some function f of xy that's equal to some constant such that the partial of f with respect to x dx plus the partial with respect of f with respect to y dy is equal to 0. Okay? Now, you haven't had partial derivatives yet. I think the only one who has is Ryan, and he's not here today. But this is the differential form of this equation. If you were to write this as in a differential, that's how it would be. Now, so here's the assumption, okay? That we know this is an exact differential equation because it fit the test. So if that's the case, there has to be an f out there so that the partial with respect to f, partial of f with respect to x has to equal, you see, this thing right here has to be that. This thing right here has to be this, because of that way this fits exactly. And that's why I said the form has to be equal 0 plus in between. That's what it's got to be. So this is saying the partial of f with respect to x is 2xy. Okay? Now, this isn't quite legal, but it's close enough. Okay? Let's write that more in differential form. Partial of f is equal to 2xy, and I'm going to change that to a dx. Now that's not quite fair, that should be partial, but the reason I'm doing that, in fact we can almost sort of make this a d here too. Okay, we're just making an assumption here, y is a constant. Okay, making the assumption y is a constant, then this would be a legal thing to do. If you integrate both sides of this, then I should pull out the y here too because it's a constant, and this would give you the integral of a perfect derivative is f of xy, okay, is equal to, and if you pulled the y out too, that would be 2y, and then the antiderivative of x would be x squared over 2. Well, now the 2's go out, okay? But this is indefinite integral, so then you'd have a plus c. But remember, c is not just a constant anymore. C might be any function of y because we assumed y was a constant. So what we'd have is some function, and usually they name it g of y. It can't have any x's in it. It only can be y. Okay? Now, that was based on this. This model here is that the partial of f with respect to x would be this. This would give it to you. Now, since that's your f, let's take the partial of that with respect to y this time. Now, this is x squared y. The partial of that with respect to y would be simply x squared, because now we're treating the x as if it's a constant, plus g prime, because the derivative of g is that. So that would be g prime of y. Okay? Now we're going to do the same trick we did before. Let's write this in differential form, only sort of making that a d, and we're doing to integrate both sides with respect to y. And again, this comes up being f of xy. Now the antiderivative of this with respect to y is merely going to be, this is a constant. So we could have moved that on the inside, so this would be x squared y. Sort of feels like we're going in circles there, doesn't it? Plus antiderivative of this, I think I'm doing this right, am I not? Would be, let me see, hold on a minute. All right, I'm sorry. I went too far. Let me back off. I knew I was going in circles there, and I said, this isn't right. Yuck. I don't know if you can see that, but it's okay. So let me erase this, and that, and that, and that, and that, and that. Okay, I went too far on this one. Sorry about that. Okay. Okay. So based on this, we take the partial with that. Well, remember, that's what this is. So this has to be this thing here, x squared minus 1, because that is your partial with respect to y. This is that. But this is the partial based on what this was. Okay? So let's take a look at that. Obviously, the x squareds are perfectly fine. What this tells us is g prime of y is equal to minus 1. Now what is that g prime of y? That's dg dy. So let's do that form. So now, this is what I meant to be doing. Then let's integrate that. And this is a derivative now. That's not a partial. Okay? and we move that to the other side, and this would be g of y. Remember, that's only of y now, is equal to minus y. Okay? Now, at this point, do not do a plus c. Go back and plug this g back in here. Yes.
Ryan said he's trying to get in the class.
Okay. Did y'all see him try to?
No, he texted me.
Okay. He's not showing up here. Do you have your code still in front of you?
No, but I can go to it.
Okay. Why don't you go to that code and send it to Ryan and say, is this the code you're using? Because y'all have all gotten in on that code, and I don't know what his thing is. Sometimes it's just like a little earlier, my internet went out. If he had a weak signal right at the time he was trying to get in, it may have scrambled something. So try that and see if he can go in again. Okay. I'll keep watching for him, but see if he used the correct code. I had a student in a class, not this class, one of the other classes. He sent me one, said, I've been trying to get in, I've been waiting, and I can't get in. And he sent me the thing that he was doing, and it was the Tuesday, Thursday class, and he was using Tuesday's code to try to get in the Thursday class. Well, they're not the same code, it changes every day. Okay, so, all right. So pick up where we are. This is our g of y now without a plus c in it. We're going to put it back in here. So your f of xy is equal to x squared y. Here he is. No, this is Jemanuel. And you did say Ryan was the one trying to get him before, right? Okay. Well, we got Jemanuel here. Okay, Jemanuel, I don't know if you can hear me yet. Were you having any difficulty getting in?
Yes, sir.
Was that yes or no?
Yes.
Yes, you were. What did you do that got you in? Just keep trying or what?
I just kept refreshing.
Kept refreshing. Okay. Kira, could you get that back to Ryan? And I'm not absolutely certain what that means, but what my guess is the internet is somewhat unstable. I know I've had a message come up in this class. I had it come up in other classes today and last week. And if you try to get in right at one of those times the internet's unstable, you probably aren't going to get in because it's just as squirrely. Okay? And if it's unstable, it may not be sending your message and getting all the digits and letters right. Okay, Jemanuel, we're in Chapter 2, First Order Differential Equations, in Section 2.4, exact equations, and we're on page 67 doing example 1. We're almost through with it. You'll have to go back and watch the YouTube video to get the full force of it. But what we're doing is going back to here, and f of xy was x squared y, and that's what I was in the process of writing when you showed up. So x squared y plus g of y, and we just found out g of y was a minus y, so that's going to be minus y. Now, that's not your solution. What the solution is that f of xy is equal to c, where c is your arbitrary constant. This is a first order differential equation, so you'll have one constant, okay, and that's it. Now, let's see if indeed this works. If you did the partial of this with respect to x, you get 2xy dx, and that's exactly what you got here. Do the partial of this with, and this is just a minus y there. It's a pretty ugly looking y. The partial of this thing with respect to y would be x squared minus 1 dy, and that's exactly what you got here. And the partial derivative of c is 0. So sure enough, that fits. This equation gives you that result. Okay, so there is our solution. X squared y plus y. Now let's see, is this Ryan? He's made it. Okay, so let me get them marked here. Perfect attendance today, folks. Way to go. Okay, Ryan, can you hear us yet?
Yes.
Okay, great. Good to have you. I don't know what goes on with signals, internet, service providers. I don't know what's going on with all these things, but there obviously is some instability in the system. Like right now, I've got 4 bars, but even with 4 bars, I had an internet unstable situation show up in this class and in an earlier class today. So I don't know why that's happening, except I think the system is just overwhelmed. It sure doesn't look like any atmospheric problems today. The sky is beautifully blue, and I don't see any wind, so I don't know why that would be an issue, but I think the system is just overwhelmed. Okay, so anyway, I don't know what you can do to improve your chances, but certainly I think you're in now just in audio mode, but I know that's where you want to be, because video takes a lot more bandwidth, and if the system is sort of shaky or something and limited, you probably are far better off being in audio only. You can see mine, but I'd love to see you, but it probably is going to hurt your reception. Okay, so what did you figure out to happen to let you get in? Do you know what happened? You just kept trying, or what?
I just kept trying. I believe I made a mistake in maybe the password or something.
Right, okay. Okay. Yeah, that happens too. So, okay. Glad you're here. Perfect attendance today, folks. Way to go. All right. Now, this is a solution. We don't need the f anymore. That is your solution. X squared y minus y equals c. Oh, by the way, Ryan, we're in Chapter 2, First Order Differential Equations in Section 2.4, Exact Equations, and we're wrapping up Example 1 on page 67 right now. Okay, that's your solution. F of x, y is not your solution, setting that equal to c, which is your parameter. That makes it your solution. Okay, now because the y is separable here, you could factor out a y on the left hand side and have y times x squared minus 1 is equal to c, and now you can write this as y is equal to c over x squared minus 1. Okay, that is also, this is an explicit solution. This one was somewhat implicit. Okay, and most of the time you're going to wind up with one like this. Most of the time you're not going to be able to solve for y explicitly. This one you could. But when you do that and set it this way, you can see obviously x cannot equal plus or minus 1, because that would make your denominator 0. But then up here, if x was plus or minus 1, that would make this 0. So then you'd have 2xy dx is equal to 0. Well, There's no reason to think dx is 0. 2's not 0, so either x or y1 has to be 0. So it's not a very interesting problem if your second term is 0. But this does give you, remember, when you give your solutions, you need to give the interval of solution. And this interval would be either anything to the left of -1, anything between plus and -1, and anything to the right of +1. Your solution's got to be in one of those intervals. It can't be in all. Okay, so that's what we've got there. All right, any questions on that? And the point is, this right here, when you get to this stage, you feel like you're through, you're not. I can't get my pen to show up. Where is it? There it is. Okay. When you get to this stage, that's not your solution. Not at all. You have to take this thing, set it equal to c. That's your solution. The f of xy was just a construct to get us there. We just sort of made it up here, though it's true, but that's not your solution. That's just whatever you find f of xy to be, that's setting equal to c, that's your solution. And they make a pretty big point about that. So let's, I guess, go back to the book for the moment here, and you'll see that's exactly what happens. I got to move y'all again. James, you're in the way again. Okay. And this is the steps we went through. Now, you could have chosen either one of these to go with. We went with this one. Okay. You could have gone with this one. That would have gotten you to the same place. A little, no better, no worse. Sometimes much better or much worse. This time it really didn't matter. So you, using this and doing your antiderivative of that, you get x squared y, treating y as a constant, plus some constant g of y. You're integrating this basically. Okay. And then you differentiate that with respect to y. And that gives you x squared plus g prime of y. You set that equal to your right hand, to your n of xy. And obviously the x squareds are the same. Subtract those off. You have g prime of y is equal to 1. That gives you g of y be minus y. Plug that back in here, and you get x squared plus y plus y, or minus y. And once you do that, then that gives you, this is your solution. F of xy is not your solution. Set that equal to c. That is your solution. And then you can solve that explicitly this way, and then it's pretty obvious x cannot be plus or minus y. So your interval of integration, you might say, cannot contain either plus 1 or minus 1. Would not be defined. Okay. And that's where they say f of xy equal that is not your solution. It's that this thing that you found here is equal to some constant. That is your solution. Okay. So let's move on to example 2. Any questions on 1 before we leave it and go for 2? Now, just looking at this, I can almost guarantee you 2 will not have an explicit solution. Okay. Do not anticipate 1. Okay. So I'm going to move you again. James, got to shift you again. Okay. And is it okay for me to clear the drawing here? Anyone need this any longer? All right. Let me get example 2. E to the 2y. That right there alone would say, nope, you're not going to get an explicit solution in y. Minus y times the cosine of xy. If that wasn't enough, I'd say that would be enough. Okay? And that is multiplied by, and written in differential form, times dx plus, and you need that plus sign there. If it's not, you change it to make it a plus, 2x e to the 2y minus x cosine of xy plus 2y dy is equal to 0. Okay? Now, even before you begin, for this to even have a chance of being exact, remember, you have to have the differential form on the left-hand side, 0 on the right-hand side, and a plus sign in between these two terms. That's the first step. To find out if it's exact or not, you need to do your test. You need to take the partial of this side, we're going to call that m, with respect to the other variable, y, okay, see what that gives you. So the partial of this thing with respect to y. Well, the derivative of e to the 2y is e to the 2y, but then you got a chain rule in there and you got a 2 in front. Okay? Everybody buy that. Derivative partial of this with respect to y. Now that's a product rule. Okay? The first part is going to be minus y times derivative of the second one. Derivative of cosine is minus sine, so that makes that a plus sine of xy. Then you've got the partial with respect, or derivative of xy with respect to y, we can give you an x. Okay, so there's your partial of m with respect to y. Oh, wait, we didn't finish, did we? Okay, plus, only it was a minus, the second time derivative of the first, and that would be just cosine xy. Because derivative with respect to y of minus y, of y would be y, 1. Okay, so now we're going to do the partial of n, which is this coefficient here, coefficient function, with respect to the opposite one, x. Okay? Now what would that be? That would be 2e to the 2y. Because with respect to x, you count the y as if it's a constant. 2, of course, is a constant. So you're taking the derivative of x, which is just 1. So it's 1 times this constant, that. Minus, and here, you don't have a chain rule. Yes, you do have a chain rule again, because you have two functions of x here. So it's the first, x, times derivative of the second, derivative of cosine, would be minus sine, so that makes this a plus sine of xy, and then the derivative of this with respect to y, with respect to x, would be y. Okay? Then you have the next term, which is minus, because this was a minus here, this times derivative with respect to x, so that would be minus cosine xy. And then derivative of this with respect to x is 0, because you count y as a constant. Now you look at these two and see, hey, that term's the same as this one. This term is the same as that one, even though this says yx and that says xy, that's the same. And this term is the same as this one. Check, it is an exact solution. Okay? Now, unfortunately, that took most of my whiteboard. So you have to check it first to make sure that you have an exact solution. Otherwise, going through the rest of this will be totally meaningless. You'll run around in circles and never get a solution. So what I'm going to do now is take my eraser, if I can get my pen to show up again. Come on, pen, where are you? There you are. Okay. I'm going to erase these. We verified it is exact, so now we can proceed. Now, these are both pretty messy looking situations here. Okay? So I guess it really doesn't matter which way we go. I wouldn't be surprised if it does matter, but we should still be able to get our solution no matter what. One way may have us working harder, but let's see if we can do it. Now, what's our assumption? Our assumption, there is a function f of xy equal to some constant c such that the partial of f with respect to x dx plus the partial of f with respect to y dy is equal to 0, because the derivative of c is 0. Well, this follows exactly this. Now, since this is just 2 terms, that's 3 terms, I'm going to try to go with this one first. So let's just make the assumption that the partial of f with respect to x would equal e to the 2y minus y cosine xy. Okay, so let's write that in differential form, and since we're going to treat y as if it's I wrote y, it's going to say y and I wrote y. Let me get this. Oh, I've got 2 different boards here. Okay, this is dx. Okay, this dx comes over here. Okay, and let's integrate this. Okay, well, this is just going to be f of xy is equal to, well, the integral with respect to x of e to the 2y, that's just a constant, so that's going to be e to the 2y times x, because that's a constant. Okay, might want to put that in parentheses. Partial of a constant dx, antiderivative of that would be x times that. Here you would have, okay, y, remember, is a constant, so it's just going to be there. You're treating that as a constant because you're integrating with respect to x. Okay, and the integral of cosine xy, antiderivative of cosine is sine xy, but then with the chain rule you have to undo the chain rule, so that's dividing by x. No, dividing by y, sorry. Well, the y's go out. That's interesting, isn't it? Okay, because that's sort of like a coefficient. It is. The y is a coefficient of that. Okay, and then you would have, because you're integrating there, you would need a constant, but the constant could be a function of y. So we'll call that g of y. That's their favorite name for it. Okay, now what we're going to do next is take the partial of this with respect to y. If I can find my pen, there it is. Partial of f with respect to y is going to be, and here we're going to have the x, now we're treating as a constant, so that would be 2x e to the 2y, taking derivatives now, minus partial of this with respect to y would be a cosine of xy with the coefficient of x, because the chain rule tells us that, and this would be plus g prime of y. Well, now that's supposed to be the right hand side, okay, because that's partial of alpha. So let's write that down. 2x e to the 2y minus x cosine of xy plus 2y. Okay, well, looky here. This is exactly equal to that, thank goodness. This is exactly equal to that, thank goodness. That gives you your g prime of y is equal to 2y. Now this is dg dy, so let me take this out and put dg dy, but then let's write this in differential form and integrate both sides, and this would be g of y is equal to y squared. Don't do a constant with this one, just y squared. That's going to be enough. That's your g of y. Okay? Go ahead and put that back in here, and this has then that x e to the 2y minus sine of xy plus y squared is equal to a constant. That's our thing. This was our f, but that f is equal to a constant, so you put that in right there, and there's your parameter, your integration parameter. Okay? Now you can check it. See if taking the partial of this with respect to x, if I can find the pen, excuse me just a minute, I'm losing my voice. I don't know if that helps, it just feels better though. Okay, here we go. The partial of this with respect to x would be e to the 2y. That part's good. Partial of this with respect to x would be minus cosine of xy times y, and there's minus y cosine of xy, and the partial of this with respect to x is 0 because you treat y as a constant when you're taking the derivative with respect to x. So sure enough, that gives you this one. Let's take this one again and do the partial with respect to y, and that would be x is just like a coefficient now. Treat that as a constant. X e to the 2y, then chain rule will give us a 2, so 2x e to the 2y. Sure enough, that's what we got there. Take the partial of this with respect to y, and you get minus cosine of xy times the coefficient x, and sure enough, that's what you got there. And take the partial of this with respect to y, and you get a plus 2y. And take the derivative of c, you get a 0. So sure enough, that is your answer. Now, do you think you can solve that explicitly for y? Don't even try it. Okay? Not going to happen. Okay? Would you be able to solve it with respect to x? Nope, not there either. This sine of xy, basically, if I could find my pen, this is going to preclude that being solved. So this is an implicit solution, and that's it. Okay? And that's about, excuse me, all you can do with it. Okay. X e to the 2y minus sine xy plus y squared, and they say plus c is equal to 0. I don't know why they turned that around and did that. I like it just fine, equals c. Be perfectly fine. Okay, for some reason I have a thing blocking my screen here. I don't know why. So let's go back to the book. All right. And now I got to move y'all again. James, get ready to move. There you go. Okay. Here's example 2. E to the 2y minus y cosine xy dx plus 2x e to the 2y minus x cosine cosine xy plus 2y dy is equal to 0. Okay. Now remember the coefficient function of your dx, that's what we call the m. this is what we call capital N. The partial of m, this is our check, remember? Partial of m with respect to the other variable, y, gave us, and we did this already, 2e to the 2y, and then partial of this term with respect to y would have been a minus of minus plus sine xy times x. So there you have it. And then, yeah, partial of this with respect to x would be treat the 2 and the e to the 2y as if they're constants, which they are. 2 certainly is, and that would just be 2e to the 2y, and sure enough you get that. And then treat the you're taking this with respect to x, so treat the x as a constant there, and that would give you a plus x sine let me see, wait, let me slow down a moment. You're taking the derivative with partial with respect to x. So that's a chain rule that you have there. I mean, a product rule you have there. Cosine minus cosine xy plus xy sine of xy and plus 0. And anyway, you get both of those. That's exactly what you get for both of the partial m with respect to y and partial n with respect to x. Okay, so therefore you know that these are your, that your m of xy would be, that thing right there would be the partial of alpha with respect to x. The n of xy right here would be your partial of alpha with respect to y. And you could choose either one of them. They chose to do the y one. I chose the x, they chose the y. They do the partial, they're doing this one right here. Partial of alpha with respect to y is equal to, let me see if I can get that to, okay, is equal to 2x e to the 2y minus x cosine xy plus 2y. And basically you integrate both sides with respect to y, this y here, okay? So the 2x comes out, and the antiderivative of this will be e to the 2y over 2. The over 2 cancels out that 2, and you get x e to the 2y, okay? Minus, okay, the x comes out, this x here comes out, and then the antiderivative of this would be sine, but you already had the minus sign in front, so it's going to be a minus sine, and you do have a 1 over x there from your anti-chain rule, you might say, and that will wipe out that x. Okay, we'll get to that in a minute. And then the antiderivative of 2y with respect to y is y squared. They didn't have to do that. Plus you have some h of x. Okay, we used g of y, they used h of x. Now, the 2's, remember, canceled out. They have you x e to the 2x. The x is canceled out here, leaving a minus xy, sine of xy, and this just gave you a y squared, and this was your plus of hy, which is your, like your constant, I mean just h of x. You're a constant up here because you're differentiated with respect to y, so your h's are constant. So this is some function of x and x alone. Okay. Now, take the partial of this thing then with respect to x, and you should get what m is, okay? We'll take the partial of this with respect to x, you get e to the 2y. The partial of this with respect to x, you get a minus y times the cosine of xy. I'm sorry, I'm losing my voice. And the partial of this with respect to x would just be 0, okay? Plus the derivative of this with respect to x is not a partial anymore, that's the exact derivative. And when you do, goodness gracious, what was that noise? Was someone sending a chat or something? I don't know. Maybe someone sent me an email, I don't know. Sure could break a train of thought, can it? Okay. Now, that was your f of xy. You take the partial of that with respect to x, you get e to the 2y minus y cosine xy. This partial of that with respect to x, 0. Okay. Derivative of this with respect to x is x prime, or dx dx. And this is supposed to be your m, your right hand side. Well, you set that in there, e to the 2y minus x cosine, y cosine xy, and you see this term and that term are the same, this term and that term are the same. And you have h prime of x is equal to 0, okay, because there's nothing else there. Well, that makes h some constant. Okay, whoa, wait a minute, what did I just do? Yeah, that's it. Didn't know it was going to fly up like that. Okay, so your h prime of x is 0, so h of x is a constant c, and that's why they had it in this form, because that's what gave it to you. Okay? Or you could have written this x e to the 2y minus sine xy plus y squared is equal to c. That would have been a perfectly good answer as well. Okay. Got 5 minutes. Let's see if we can get example 3 done. And this is an initial value problem. Let's see what we can do with that. Okay. Gonna move y'all out of the way. Miguel, you're in the way again. Let's get you down here. Y'all can't see that, but I can. Anyone need that on the writing on the slide anymore? I hope not. I'm about to erase it. There it goes. All right, let's do example 3, I think this is. I hadn't turned the page yet. Here it is. This is not written in exact form. This is written dy dx is equal to xy squared minus cosine x sine x over y times 1 minus x squared. Okay. Now this is an initial value problem, so its initial value is y of 0. When x equals 0, y is equal to positive 2. Okay. I'm going to put the book aside. All right, this has some more maneuvering we have to do. Okay, now you might check and say, can we solve this by separation of variables? No, not quite. Okay. Certainly the denominator separates well. The numerator, however, does not. So no, this won't work for separation of variables. So here's what I'm going to do. I'm going to cross multiply, so to speak, here, and say, I'm going to write it this way: x y squared minus cosine x sine x dx, that's these two multiplied, is equal to y times 1 minus y squared, it's 1 minus x squared, dy. Okay, well, I need to subtract this from that side, so this is going to make it x y squared minus cosine x sine x dx minus, I don't like the minus, I wanted a plus. So to make this a plus, I'm going to flip these two over and make this y times x squared minus 1. That negates this, and it'll get rid of that minus sign. Dy, and now that is equal to 0. You've got to have it in the form. Whatever your m of xy dx plus n of xy dy equals 0. It's got to be a plus in between there. And we have it now. It would have been a minus just moving this over, but if I flip these two over, then that made it back to a plus. And you have 0 left on that side. So, first step, we got to see if this is an exact equation. We at least have it in the form of that, but we don't know if it's exact. Okay? So we'll do the partial of this m, this thing here, with respect to the other variable y. What would that be? Well, that's xy squared. The x you treat as a constant, so it'd be 2xy minus, and the partial of this with respect to y is 0 because there's no y in that. Okay, now let's see what the partial of n is with respect to x. Okay, well, the y we treat as a constant, and that would be 2xy, because minus y give you absolutely nothing. These two do match, so therefore it is an exact equation. Okay, but the bad news is we've run out of time. Sorry about that. These problems sometimes take a while, and I took too long at the beginning talking about the future, elections, and going back on campus and that kind of stuff. So anyway, with that done, let's pick up next time. Somewhere here I've got an eraser. Somewhere here I've got a pencil. So we have started example 3, but we are not, all we got is that the partials were the same. Now they put the minus sign with the x, I put it with the y, so it's we got that. So we'll pick up at that step next time. We've already verified it is exact. Let's see if we got enough done for any homework exercises. I bet so. Think you could do any of the odds 1 through 19. Okay, and is this our first initial value problem? I think it is. So let's hold off on the initial value problems until we finish some more. Okay, so any of the odds that are in the back of the book 1 through 19, and that will be it for homework for next time. Any questions? Sorry, my throat is giving me problems again today. No questions? Well, then I'm going to stop sharing. I'm sick and tired of sharing here. So let me end the sharing. And unless you have some last minute questions, I'll go on and end the meeting for us all. So anything at all. Okay, and I'll be ending it, and we'll see most of you tomorrow, 3 of you tomorrow, and all of you on Wednesday. Okay? Take care. See you then. Great attendance.